Hello everybody and welcome to the 8th lecture of MHM 420 780 MUA 782. In our previous lecture we talked about four boiling regimes. We talked about natural convection boiling, nucleate boiling, transition boiling and film boiling. And we said that in this lecture we are going to talk about correlations, or how we are going to calculate the Q dot boiling or H, which is the boiling heat transfer coefficient, because at the end of the day we want to use those numbers. We want just to also know how we can calculate this heat flux maximum at point C, how we can calculate the Leidenfrost point. Okay. So first, let's start with natural convection boiling. So natural convection boiling, when it happens when the delta T axis is between 1 to 5. So we are talking about it, natural convection boiling. What does it mean? It means that boiling in this region, or when the delta T axis is between 1 to 5, boiling is governed by natural convection current. Heat transfer in this case can be determined just using natural convection relations. So whatever relation that we need to go to chapter 9 of the textbook and we can find it. Okay, so because we don't want to make you confused, let's solve one example and let's see, when we are saying that it is natural convection boiling, and go to the chapter 9 and solve it, what we are referring to. The example is here: the surface of a horizontal 20 millimeter diameter cylinder is maintained at temperature of 104 in saturated water at 1 atmosphere. Estimate the heat flux. So as I mentioned, wants to know the heat flux. The Q dot basically is Q dot boiling, which is natural convection boiling, is requested. Okay, so first what we need to do is we want to calculate the delta T axis. Okay, because here we don't know, there is nothing mentioned about the natural convection boiling. First we want to know that what regime of boiling we are talking about. Okay, let's calculate the delta T axis. Delta T axis is like, we know the temperature of surface is 4 minus T saturation of liquid, but do we know it? I can't see it here. So how we are going to find the T sat? Saturated water, 1 atmosphere. We go to the table, we read it. Okay, so when we read it, say that it's minus 100, so we have 4 degrees. Okay, so now we know that, or we confirmed what I said at the beginning. The boiling regime that we are dealing with here is natural convection boiling. Okay, natural convection boiling. How we are going to solve it? So the first step would be defining the properties. Am I right? Because without having the property, we can't use any of those correlations. So we go to table, if I'm not mistaken, A6, and we just read some of the properties. But at what temperature? Because in order to read the property from the table, we need temperature. Am I right? So at TF, which is TS sat plus TS surface divided by 2 is equal to 102. If we go and read it from the table at 102, we need to find rho L, which is the density of liquid, kilogram cubic meter. We need to find CPL, which is joule per kilogram Kelvin, mu L. We need to find KL, to find Prandtl and beta. This is the unit is 1 K. Prandtl is dimensionless and KL is unit watt mk, and mu L viscosity is SM2. So we read those properties from the table at 102 Celsius. Now, okay, natural convection. So how we are going to do it? It looks complicated. No, it's very simple actually. Why? Because we know that in order to find the Q dot what you need to find the Q dot, you need to have the H. Why? Because the delta T excess, you have it. So if you find H, you are set. How you can find H from natural convection? So first you need to find Nusselt number. From Nusselt number, correlations, they are differ. Some of them you need to find Reynolds, some of them Rayleigh. So because natural convection, so Rayleigh number. And after that, when you find the Rayleigh number, you can find Nusselt number. When you find Nusselt number, you can find H. Okay? So let's see how we can do it. I'm not going to solve it like by putting all the correlations, but if you go to your textbook and chapter 9 and see a correlation calls the Churchill-Chow. It's very a famous one. So basically it's saying that Nusselt D is equal to H dk and is equal to 0.6 plus 0.387 Rayleigh D to the power of 1/6 divided by 1 plus 0.559 divided by Prandtl to the power of 916 827 to the power of 2. You might say that what kind of correlation it is. Yes, I told you, semi-empirical or empirical correlations. They are not based on the very clear physical explanation. They just did some kind of experiment, and after that they use this kind of correlation to fit those data. That's the reason you see that 0.787. There is like a constant in front of the Reynolds, or to the power of 1 divided by 6. Why not 1 divided by 7? It's semi-empirical. Okay, so how you can find this one? So Prandtl, we calculated or find it from the table or read it from the table. It was easy. The diameter is given, K. We read it from the table. So the only thing that we need to do is finding Rayleigh number. Rayleigh number is G beta T3 alpha. So again, D we have it, delta T we have it, beta G we know it. What is this 2? Alpha we know that alpha is equal to K divided by rho Cp. Cp we have it, rho we have it, K we have it, we find this one. How about here? First we need to find what is this one. What is it? Because if you remember previously, when we went to the table, we just read Newton second per square meter. Basically, this one is divided by rho. Just keep it in mind as well. So you can just read this one from the table, divided by rho, you have this one. Multiply by alpha, you have all those numbers. So I just write the process. Please go home and do it. So you have the Rayleigh, you put the Rayleigh, you calculate the Nusselt number. Okay, when you have a Nusselt number, after that you calculate H. When you have H, you can easily calculate from Q dot is equal to H delta T. You can calculate Q dot. Okay, so it's basically, I didn't want to solve an example. I just wanted to show that when we are saying that for section natural convection boiling, when we are saying that go to chapter 9, what does it mean? First, the first step for you is to calculate delta T excess to see that what kind of boiling regime we are talking about. Okay, after that you are going to find the right correlation based on every single boiling regime that we talked here. For natural convection boiling, when the delta T excess is between 1 to 5, the same example that we talked about, you go to chapter 9 and you find the answer. Natural convection, so it's convection heat transfer. We know that it's based on the property Nusselt. There are some correlations that you can find Nusselt. Rayleigh number, from the Rayleigh number you find first you find Rayleigh, you find Nusselt, from Nusselt you find H. When you have H, you can easily calculate the heat flux. But let's say, okay, now the temperature is higher than 5. We talked about natural convection boiling. Now is delta T excess is between 5 to 30. It's nucleate boiling. What are we supposed to do? For this section, we have a correlation here. It's a correlation that you can see here for Q dot nucleate. It's when the delta T excess is between 5 to 30. We can use this correlation, and each of them being defined here. You see that viscosity of liquid, enthalpy of vaporization, density of liquid, density of vapor. You see all those units as well. Surface tension, specific heat, liquid surface temperature, saturation temperature, experimental constant, which depends to the surface fluid combination, Prandtl number, experimental constant. So you see, again, this correlation is based on experimental results. So it's not very accurate physics behind it. It's normally based on semi-empirical correlations. So a little bit of experimental data, a little bit of physics and what's happening in nuclear boiling, and they came up with this correlation. But it's this correlation was suggested in 1952 by Rohsenov. It's I think, if I'm not mistaken, a Russian scientist. And then, as I told you, because the nature of especially this nucleate boiling is very complicated. Why? Because we are not completely understand how nucleate sites start from like a specific place or at a specific temperature. How about the boiling, the bubble formation? It's very complicated. So all of them are very difficult. So I cannot predict how many nucleate sites we can have by knowing the temperature or the surface, or I can't predict where the first bubble will form, or how the bubbles will behave. That's a reason that it's very complicated to understand the nature of nucleate boiling and come up with a correlation or any kind of mathematical correlation for heat transfer based on theory, like a pure theory. So that's a reason we rely on these semi-empirical correlations. So we solved one example for natural convection boiling. Let's solve one example for this one as well and see how does it work in this case. It's the same as previous one. I'm not going to talk extensively about it, just a little bit. So water is boiled at sea level in a coffee maker equipment. The size is given. It's an electric heating element, so we know that the temperature is the coffee maker initially contain the volume is given 1 liter of water. The temperature is 14. Once boiling starts, it is observed that half of the water in the coffee maker evaporate in 25 minutes. Determine the power rating of the electric heating element immersed in water and the surface temperature of the heating element. Also determine how long it will take for the heater to raise the temperature on 1 liter of cold water from 14 to the boiling temperature. So here is a little bit critical for us. Why it is critical? Because the question is asking us to determine the temperature of the heating element. When we don't have the temperature of heating element on its surface, we can't really calculate the delta T excess to know what kind of boiling heat transfer or what kind of flow regime we are talking. That's the situation that you might face during the exam as well. You might say that, oh sir, I don't know anything about it because I can't calculate the delta T excess. But what you do is, first you make an assumption. You say that, okay, I'm assuming that the boiling regime is nucleate. You solve everything, you find the temperature of like a heating element or temperature of surface. After that, if you find if that temperature satisfies the condition of nucleate boiling, which means delta T excess between 5 and 30, it means that your first assumption was right. If it was lower, you go one back to natural. If it was higher, you go one up. So it's don't panic. First assume something, and after that try to see if your assumption is right or wrong. But in this case, we are assuming that it's nucleate boiling. In fact, we know it is nucleate boiling, but in this case, we are just like going to pretend that we don't know anything, so we are assuming that is nucleate boiling. So nucleate boiling, we go to this correlation. You see that all these properties we need to read from the table. Okay, but But the problem is sometimes you might say that, okay, at what temperature? Should I just read it at any temperature that I want? What do you think? Any idea at what temperature you need to read? Okay, for nucleate boiling or this Q.nucleate, you need to read the properties at saturation temperature. So here we go to the table and we realize that the saturation temperature is 100. So Tsat is 100. From the table we read rho L, rho V, sigma, Prandtl, HFG, mu L, CPL. So we read all those values from the table. I just write it down, but some of them I'm going to write it down, but you need to do it yourself at home. This surface tension can be found from another table, I think, if I'm not mistaken, table 10.1, 0.0589 meter, Prandtl, and all those other numbers. So you read them from the table. If you remember here, we mentioned about two constants. One was CSF, experimental constant, that depends on surface fluid combination, and N is experimental constant that depends on the fluid. So how you can find that? There is a table 10.3, if I'm not mistaken. You go and you find it. So CSF is equal to 0.0130 and N is equal to 1. Okay, now we have everything. You put it into the correlation and you find Q.nucleate. Can you do that? No. Why? Because you don't have the T surface. So you have this one, you have this, you have this, you have this, you have all of these ones, but what you don't have TS. How you are going to sort it out? There is another information that is given to us as well. Let me just go back to the question and show it to you. There is something like evaporation. Once boiling starts, it is observed that half of the water in the coffee maker evaporates in 25 minutes. Okay, so do you think, can I say that Q is equal to Q dot delta T is equal to M HFG? So Q dot is equal to M HFG divided by delta T. Delta T in 25 minutes. So this needs to be in seconds. M, how we find M? Because it's saying that it like half of the water. So 1 liter divided by 2, half a liter, it's water. So half a kilogram. 0.5 kilogram. HFG, we read that from the table. So Q dot is 0.7523 kilowatt. That is what the question was asking. But is Q dot, there is a difference because what we find Q dot nucleate, if you see here, let me go back to the correlation, there is no A, so there is no surface area here, so keep it in mind. This one was Q dot, here is Q, capital Q dot, kilowatt, but this is lowercase Q dot, units are different, so this unit is square meter. For this one, so Q dot, we calculate AS, and after that Q dot will be 299.360 kilowatt, sorry, watt a square meter. So we put this one as a nucleate, is the same, and we can find TS to be 112.9 C. So now let's check and see if our first assumption was right. Yes, so delta Txs is equal to 11.2, which is between 5 and 30. So our first assumption that the boiling is nucleate boiling was correct. Okay, but please do it at home. I just explained a little bit, I didn't solve it properly, so you do the same as well. Just go through it and try to see if you can solve it. But the process is simple, as I told you. First, what you do is first you calculate the delta Txs. If you can't, as I mentioned, first you assume a value or number. After that, you calculated the T surface, and at the end you compare it and you examine if your first assumption was right or wrong. And there is a correlation, semi-empirical correlation is an open textbook. You don't have to remember it by heart. You just open your textbook, you write it down, you see that all the information there needs to be find from the table, so you go and read it, read from the table, you put it, you find the Q dot nucleate. Okay, so we talked about natural convection boiling. We also talked about nucleate boiling. If you remember, I told you that nucleate boiling is the desirable regime of boiling for us. Why? Because the maximum heat flux, if I mention here, the maximum heat flux happens in nucleate at the end of nucleate boiling. So this area, close to this point C, it's very desirable for us. We want to design everything that we have to achieve the highest heat transfer to that specific point. Even though the nature of boiling heat transfer is very complicated and most correlations are empirical or semi-empirical, but to find the maximum heat flux, we have a theoretical calculation that was suggested by Kutladze in 1948, another Russian, and there is a correlation for it to find that point. So here, as you can see, but before just speaking about the correlation, there is a small mistake in the textbook. Please go and correct it. As you can see here, the one that it's rho to V basically is correct. This one is not correct. This is wrong. This is the correct one. I think it's just a typo in your textbook. I don't know what kind of edition you are using. If you are using edition 3, I think the majority of you will have this mistake, this typo here. So basically is the density of vapor to the power of 2. Density of vapor to the power of 2. So basically you see it's much easier than the Q dot for nucleate, CCR, HFG, surface tension, gravity, density of the vapor, density of liquid, density of vapor to the 0.25, the power of 0.25 at point C. So at when delta T excess is 30, this correlation should give you the same answer as this correlation. So basically at delta T excess is equal to 30, this should give you the same answer as Q dot max. Why? Because at 30 both of them are the same. Okay, so now we know this correlation. Just keep in mind this mistake. So the only thing that we need to do is we need to go and find let me just put the right one here. We need to find enthalpy of vaporization from the table. We need no gravity, no need. Density of liquid, no need to go to the table. We know the value. We need to find the density of liquid from the table, density of vapor from the table, and after that surface tension of liquid vapor interface from the table, and we will be set. But there is a constant here, CCR. This constant depends on heater geometry, and you can read it from table 10.4. Yeah, basically that's it. Okay, so there is another important point at the end of nucleate at the end of nucleate boiling, that we can't really design, because I said that you get to the maximum, but immediately after the maximum you go down. So what you want to do is you want to be on this side when you want to design something, instead of going to the other side. So it's very important that to keep it in mind that a little bit less than C is much more desirable compared to a little bit after point C, because with the less delta T excess you are getting exactly the same results. Okay, but of course it's very difficult to control the temperature in a way that all the times you are exactly at point C and the maximum number. Okay, after the nucleate boiling, now we talked about the correlation. The next regime is transient boiling. For transient boiling, there is another correlation, as you can see here. So we find basically Q dot minimum or Leidenfrost. There is a semi-empirical correlation. Again, is based on enthalpy of vaporization, gravity, density of liquid, density of vapor, and surface tension of liquid-vapor interface. So we go to the table and we read those numbers and we put in the correlation and we can find points minimum. But let's say you might say, okay, what will happen between point D and point C? So basically, when we have point C from Q dot max and we have Q dot minimum at Leidenfrost point, we can assume that this is a linear, it's a line between these 2 points. So if something is in the middle, we can do interpolation. Okay, so let's just like go to this one. There are, I put it here in one correlation to show you everything. So for natural convection relations, if you remember, I told you, you go to chapter 9. For this yellow section, which is the nucleate boiling, we have just one correlation. For Q dot max, we have one correlation that you use. For Q dot mean, we have another semi-empirical correlation, but we know that this Q dot mean minimum for Leidenfrost points and Q dot nucleate, they were semi-empirical correlations, but not the Q dot max. At point C, Q dot max and Q dot nucleate should give the same result, which is delta Tx is equal to 30. I think basically that's everything regarding the nucleate boiling, transition boiling, and after that from point E, what will happen is we talked about it, the process that what will happen after point D is not desirable for our designs, and there is no correlation for it, but still again we can assume that is linear between D and E. But if you remember, we talked about another between D and E, we said that it's film boiling. How about the film boiling? For film boiling, we have another correlation. Here you can see that Q film is another semi-empirical correlation. C film, that is depends to the shape, thermal conductivity, enthalpy, gravity, density of liquid, density of vapor, surface tension, the surface temperature, saturation, viscosity, specific heat of vapor. So just think about when we are saying that here specific heat of vapor, if you read for liquid, everything will be wrong. Okay, so just give detailed attention to these properties, the thermophysical properties that you are reading from the table. Make sure that you read them at the right temperature and the right values. But here you see that we have the Q dot radiation and Q dot total. Why? Because we said that radiation cannot be neglected in film boiling. Why radiation cannot be neglected in film boiling? Because of the high temperature. When we are talking about the surface that has, for example, 800 degrees, we can't forget about radiation. Okay, so that's a reason there is a correlation. You calculate Q dot film. There is a very simple calculation. You calculate Q dot radiation, and Q dot total for that section is Q dot film plus 0.75 q dot radiation. Okay, but again, if you remember, I told you about at what temperature, so because here you see that you have liquid, you have vapor. So for example, when I want to read the density of liquid, at what temperature I should read, because let's say saturation T sat is 100, T surface is 800. It's not close to each other, it's very far from each other. At what temperature should I read? How about the density of vapor? At what temperature? So it's very important to know that the vapor property, when we are talking about film boiling, the vapor properties should be evaluated at film temperature. So vapor at film temperature, what is film temperature? Is equal to Ts plus Tsat divided by 2, the average of it. But liquid properties, anything related to liquid needs to be read at liquid temperature, which is saturation temperature. Okay, so I think basically that's it. We talked about why we added that radiation because of the high temperature. We also said that Q dot total is Q dot film plus 0.7 plus Q dot radiation. So okay, the other thing that we need to keep in mind is that all the correlations that we discussed here so far for boiling heat transfer are applicable to smooth surfaces. Now I want to discuss a bit about what are we supposed to do when the surface is not smooth, and answer the question that which one is more favorable for us. Do we really like to have a smooth surface or not? If you remember, I told you during our last session that the rate of heat transfer in the nucleate boiling regime strongly depends on the number of nucleate sites and the rate of bubble formation. Okay, so if we have more nucleate site, it means that we have a higher heat transfer rate, the same as bubble formation. Higher bubble formation, higher heat transfer rate. So what does it mean? It means that any way that we can increase the number of nucleate sites, any way that we can increase the rate of bubble formation, will end up increasing the rate of heat transfer. So then it is proven that roughness of heating surfaces will serve as additional nucleation site and will result in higher heat transfer rates. So in this case, actually, the roughness of the surface will help. I mean, if I want to give you an example, so I'm sure you are a student. I was a student like you now. When you go to the dormitory and you go to the kitchen, it's really difficult to find a nice pan. All the time are sketchy, like, you know, lots of people, they used it. You can see the lines in the middle of it. Actually, if you put water on that, you see that those lines that you see in the middle of the pan, those are the first places that you see the bubble formation. So that's the reason. So rough surfaces actually helps and increases the bubble formation rate. But now if we want to talk, okay, how it's like related, can you give me a kind of correlation or some kind of relation to say that how roughness is related to nucleate boiling regime. It's not something that we can discuss for the undergrad, but just keep in mind that one researcher called Branson showed that heat flux in nucleate boiling regime can be increased by a factor of 10 by roughening the heating surface. So just think about that. By roughening the surface, you can get sometimes 10 times higher Q dot or heat transfer rate for nucleate boiling regime. So now let's say I'm telling you this information. What are you supposed to do? You said that, okay, now you told me about this roughening the surface. What am I supposed to do with this information? What do you think? There are two reasons for it. One is that those high heat transfer rates due to the surface roughness are not sustained, will appear very fast. So having high heat transfer rate for a moment cannot help a lot. So again, we said that high, but let's say in 1 second. We are not talking about that specific second. So in reality, maybe it doesn't change a lot. The second one is that the surface roughness on maximum heat flux, which is happening at point C, won't affect it. And since the design stuff for point C, where we always design things for point C, we achieve point C, and that point will stay the same regardless the quality of the surface. So just think about it. We talked about the roughness, but at the same time I asked the question that, okay, when I talked about roughness, surface roughness that will increase it, why not all the pans are rough? Why all smooth? So people, they don't know it. It's like, it's very simple concept of heat transfer and mechanical engineering. Why they didn't design like pans with the rough surfaces? So, and we said that first, one of the reason is that we said that the rate of heat transfer will increase, but it's not sustained. So it will be like maybe 1 second or 2 seconds very high, but not all the time. And the other point is, we said that everything in boiling, we designed it for this point C, which is not even close to the film boiling. Okay. There is I think the information that we have provided is enough. Let me see if we have enough time to solve one example or not. So I think we can solve one example, even though we will go a little bit over the time, but I think it's not a bad idea to solve one example here. So I'm going to solve this question 10.39 of the textbook, and we want to see how we are going to use this Q.film, as we mentioned previously. It's a 2 millimeter diameter cylinder metal rod with emissivity is given. Why emissivity? We said that for film boiling, we can't neglect the effect of radiation, so we have emissivity. We have the temperature. So now we want to find the power. So let me just like speak about it here, okay, now we need to first we write down the correlation. Let me just like quickly write the correlation. Q dot fill, C fill, G K V to the power of 3 rho V rho L minus rho V, HFG plus 0.4 CPV TS minus TSAT divided by mu VD TS minus TSAT. This is to the power of 1/4 and everything multiplied by TS minus TSAT. Sorry, it was not like enough space to write it nicely, but you have the correlation, so you don't need me to write the correlation here. So the only thing that we need to do is to find TSAT, to find the property when the put it into the correlation. So we go back to the question. We see that okay, we have the TSAT 100, we have T surface 500, we have those two. If you remember, I told you the vapor is going to be read at film temperature, and property of liquid at liquid temperature, liquid or saturation temperature. So T film is equal to 500 plus 100 divided by 2, 300 degrees. So when we go to the table, we read everything that related to vapor: rho V, CPV, KV, mu V. These are, we read them at 300. What are we going to read at liquid temperature or saturation temperature is HFG rho L. Okay, so we have all those things. We have T S minus T sat. So if we put everything, Q dot film will be equal to 1.152 10 to the power of 5 watt square meter. Please give extra attention to these like temperatures that you are reading properties from. Lots of points will be missed if you make a mistake here. Why? Because let's say if you read at wrong temperature, everything else after will be wrong, because first all these properties will be wrong, so you won't get any mark for them. When you won't get any mark for this, you won't get any mark for Q dot film as well. So sometimes students for average, I seriously like wrote 500 minus 100 divided by 2. Why? Because they were in rush, they didn't pay enough attention. So be careful regarding that stuff. So we calculated the we wrote the Q dot film 1.152 multiplied by 10 to the power of 5 watt per square meter. Now we have that, but we also, if you remember, we said that radiation cannot be neglected for film boiling. So Q dot radiation, it's like we know it is epsilon sigma Ts minus Tsat to the power of 4. So this is given Stefan Boltzmann. We have two temperatures to the power of 4, so we have 9573 watt square meter. This is Q dot radiation, and Q dot film was 1152 10 to the power of 5 meter square meter. So Q dot total is equal to Q dot fill plus 3 divided by 4 that radiation it will be equal to 1124 10 to the power of 5. And we go back to the question that we see what else is asking. Determine the power distribution per unit length of the metal rod. So basically it's asking us Q dot total divided by L, so which is asking us watt per meter. We have watt per square meter, so it will be Q dot total multiplied with that pi d, and the answer will be 769 meter. Okay, so basically that's it. This is but do it at home to just like have a better understanding how to use those kind of correlations. They are very simple. The correlations are given after you calculate the delta T excess and you know that what kind of boiling you are talking about. It's very easy. The only difficult part would be going to the table and reading the properties at the right temperature and right table. So if you don't mix that one, or you make a mistake there, everything will be very simple, and just like put those numbers into the correlation and you will get the answer. Okay, it was the end of lecture 8, and we are going to continue next week with lecture 9 and the same, and we are going to talk about boiling and condensation, and we continue the same topic. Thank you for your attention.